noted the uncharacteristic jacket. Now, if you've seen it, I'll take it off. I see I've already made a mistake. My name is bigger than MIT, which is clearly undesirable. Thank you for coming. Thank you, Peter and Louis, for inviting me. The work that I'm going to describe is not my work. It's a work of a considerable research group who I'd like to introduce: Steve Crouch-Baker, Nada Jessica, who's just joined us, Stuart Smedley, Brent Ken Zeller, Mark Williams, and Sharon Wing, the group of people currently working on this project. Arthur Schreiber and Romeo Rocha have left the project and gone other places, and Andy Riley was killed on January the 2nd of this year. Funding is provided, very gratefully acknowledged, by the Electric Power Research Institute. And in addition to funding, the Electric Power Research Institute has provided considerable technical contributions to this project in the person of Tom Passel, Joe Santucci, and Bob Weaver.
Mark, about 3 dB more.
There seems to be an electrical fault with the microphone, but I can show. I'm just going to give you a little overview of what I hope to present here, and I have a tremendous amount of information.
Could you try a little fine focusing?
Is the lights down too?
Complaints. How's that? As we're going through these iterations, the announcement by Sandmans and Martin Fleischmann in March of 1989 took us all by surprise. Some were more stunned than others. As it happens, I have been working on the hydrogen-palladium, deuterium-palladium system for about 13 years at that stage. And it occurred to us at that stage that in order for anything that was being claimed by Fleischmann and Barnes and by Jones about the deuterium-palladium system to be true, it had to be true under extraordinary circumstances of that system. And our hypothesis, the hypothesis that we set out to test experimentally, was that in order to produce this anomalous effect, or any anomalous effect in the system, it had to be done at very high deuterium to palladium ratios, very high loadings, as we will describe them. This is a circumstance under which the DPD system is not well studied, has not been well studied, and anomalies potentially could occur. We embarked upon an experimental program at SRI to test this hypothesis, and our experimental program was really determined by an attempt to understand this explanation, not an attempt at replication, because we didn't study newspaper articles to try and find out what the geometry of the Fleischmann-Barnes cell might be. We simply took the idea that if the deuterium-palladium system was producing this anomalous effect, and if this anomalous effect would be produced at very high loadings, what would we do to produce a highly loaded system and examine the system for anomalies? Our experiments were based upon our own experience. That is, we used our experience in creating high loadings and monitoring the loading of the deuterium-palladium system using resistance ratio and AC impedance methods in order to establish this experimental program. And the idea was that we would obtain scientifically useful results, whether or not replication was successful. What we know today, and what I hope to lead you to towards the end of the lecture, is that we can demonstrate that there is, under special circumstances, a substantially larger energy out in the experiments as determined by calorimetry than there is known sources of energy put into the experiment. Obviously, and consequentially, the output power under special circumstances is larger than the input power, And I will assert, and not have time to demonstrate fully here, that that excess power is larger than the measurement uncertainty by numbers like 20 sigma, 30 sigma. There is a very strong observed correlation between the excess power and the deuterium to palladium loading as determined by the resistance ratio. We do not see, have not seen, quantitative nuclear products. And the condition that we're at now in our understanding of this anomaly is that the effect is either real or it's some obscure artifact, and perhaps an artifact that must change from experiment to experiment. The observations that we make are larger by at least 2 orders of magnitude than the known chemistry of the contents of the electrochemical cells. Our experiments were divided into 3 groups, and I'm really going to concentrate on the heat results today. But in order to obtain excess heat in these experiments in our hands, one must achieve deuterium to palladium loading ratios in excess of a value of something like 0.9. So at least a third of the experiments that we have performed have been intended to address the issue of how do you get deuterium into palladium, how do you keep it there, how do you monitor it and maintain it in this high activity state for considerable periods of time. I have on this slide the experimental parameters of this set, and I'm going to describe them no further than to say that in order for us to obtain and maintain high loadings, we must form in situ on the surface of the palladium cathode in its alkaline electrolyte a film where the constituent parts of this film contain the elements either silicon or aluminium, and others may be possible. Our conclusions are somewhat at odds with some electrochemical conjectures in the last few years, but by no means at odds with the known electrochemistry of the hydrogen-palladium system in the 20s, 30s, 40s. By careful control of the electrode pretreatment, the electrolyte composition, and the current density, it is possible to attain and maintain the high loadings, deuterium to palladium ratios, approximately 1, that are necessary to produce the anomalous effect. I'm going to talk about loading quite a lot, and I'll correlate my results somewhat with the deuterium to palladium atomic ratio. In our experiments, the primary tool for determining the loading is the resistance ratio. Here I have a plot of the resistance of a piece of palladium as hydrogen or deuterium are introduced into the atomic lattice. The resistance ratio goes through a maximum at a value of about 0.7. And these data here, the green points, are extracted from the literature of gas loading experiments by Baranovsky at very high pressures, multiple gigapascals of deuterium pressure. And we infer our loadings from a measured resistance ratio. So we are requiring the resistance ratio has gone through its maximum, is on the right-hand side of the maximum, a fact that can be determined from the derivative of a parabola being more or less a straight line. If we increase the current or increase the hydrogen pressure and the resistance ratio goes down, then we can fairly easily determine that we are on the right-hand side of that maximum. So we're looking for high loadings as determined by the resistance ratio. I'll spend most of my time today on the calorimetry. We've done something like 30 experiments in an isothermal flow calorimeter. Several designs, low pressures of deuterium gas, medium pressures 1,000 psi, high pressure 10,000 psi, covering a wide range of current densities, incorporating a wide range of operational powers. And one of the key features of these experiments is that they're very long. They occupy 1,000 to 2,000 hours, 1 to 3 months. We've observed unaccounted for excess powers on 40 occasions in the 2.5 years of experimental program, in which we characterize 2 basic categories. A baseline excess, these are not our terms, and they're not the terms that I would have chosen, but they're used by the community. Baseline excess is a small effect, 1 to 30% of the input power. It initiates and terminates under the control of the experimental variables the variables that we have control of, the current density, the temperature, and X, the loading, the G to PD ratio. The effect is relatively causal, it's reproducible in a sense, it's predictable, we can determine the conditions under which it will be seen, or should be seen, and will not be seen. Can be controlled by control over the current density and the temperature which control the loading. We've seen this effect 38 times. Because it's so small, it may be of no more than scientific interest, or it may be that this effect itself might be enhanced. The important feature of the baseline observation is it continues for very long periods of time and apparently only terminates when we choose, either deliberately or by experimental clumsiness, to terminate the observation. So the power will stay in excess for periods of time. The longest observation is 8 days. Peak bursts, these are large effects, greater than 300% of the input power. They appear to initiate spontaneously. Clearly they don't initiate spontaneously, they themselves must be causal. We don't know what the parameters are that initiate these heat bursts. They are relatively insensitive to current density, unlike the baseline excess, and may even survive small amounts of anodic charge, that is stripping, reduction of the deuterium to palladium ratio by electrochemical means. May or may not appear in conjunction with the baseline observation. Fleeting, we have observed this effect only 3 times. Chaotic, meaning that we don't know what parameters initiate this effect. Because the effect is large, however, it may be useful in terms of a power generating device, which is what my sponsors principally would seek. It's Peter's idea that at this stage, everybody's starting to drift off, so I'll show you a picture of what excess power looks like in its manifestation in our experiments. Here we have a ramp of current in a cell of area about 3 square centimeters, a ramp up to 500 milliamps per square centimeter, and then it will be on. Period of time preceding this, where the calorimeter was in thermal power balance, which unfortunately the calorimeter most always is in power balance. We observe an excess, in this case of 1 watt, up to something like 2.5 and 3.5 watts excess at a time when the input power was 12 watts. So we're looking at an effect of 10 to 30% excess power, where the jaggy line is the raw data, and the heavy lines are the data with the compounded measurement uncertainty of the experimental variables applied to it. So we know the excess power to be this number, plus or minus this bound. And if we look at the integral of that observation to measure the excess energy during that period of time, we look at the time scale of 150 hours or so, fairly prolonged observation. We see an energy, again with its assigned uncertainty, and here a representation of that as a fraction of the input power. So a number getting up to 10% of the energy applied to the system at that time as a consequence of the excess power that we observe. So we have an excess of half a megajoule with an assigned uncertainty, which is 8.5% plus or minus its assigned uncertainty of the input energy. This is what the effects that I'm going to describe look like. The baseline observations themselves appear with a reproducible pattern, and they are observed if a minimum of 3 criteria are met. The deuterium-palladium ratio must achieve a critical value, a value something like 0.9 D to PD. Above that, there is a parabolic or possibly exponential increase, and I'll show you some plots of that functionality later, with increase in loading, possibly asymptotically reaching an asymptotic limit at a value of loading of 1, possibly. Not only must we achieve this loading, and this loading is relatively easily achieved and relatively quickly achieved, must be maintained for a critical period. That period is about 300 hours for a 3mm diameter rod. It's less for foils. But the important feature here is that that critical period is longer than the diffusional time constant of hydrogen and its isotopes in palladium. It's of the order of the diffusional time constant of other light elements such as lithium in the palladium, but it is not a feature of the diffusion of hydrogen in the lattice. Not only you must attain the loading, you must maintain the loading. And you also must have a certain current density. And the critical value in our experiments is about 200 milliamps per square centimeter. So you can turn the effect on and off by going above and below this current to the threshold. This is not a very well-defined threshold. It tends to reduce in value with increasing exposure of a particular electrode. It is not my purpose to talk about our nuclear measurements. We did monitor online neutron and gamma rays, did some experiments looking for X-rays, things that are relatively easy to do and not looking at low-level detection. All we can say is that these nuclear products, energetic nuclear products, are not present, quantitatively correlated with the excess power. We autoradiograph our electrodes after exposure to look for any evidence of low-energy ionizing radiation. In one experiment, we did have some possible evidence, some exposure of the film. I'm not going to talk about that any further. We've done probably 500 determinations of tritium in our experiments. In no instance have we ever seen tritium enhancement. The search for helium as a possible product or isotopic shifts, all I can say is that we have searched for these, and in none of the experiments have we seen strong evidence of isotopic shifts or helium production, and in none of the experiments that we have performed have we produced enough energy in the volume and mass of materials that are present that we would expect to have been able to observe these as products of nuclear reactions. This is a controversial subject. Controversial, and its controversy varies from place to place. The reason for this controversy, it seems to me, is that we're dealing with two belief systems. We have a belief system based upon hope. People hope that cold fusion is a reality, is an answer to the world's energy needs. It's a perfectly legitimate belief and a reasonable hope. There's a belief system based upon experience, the experience obtained of nuclear processes in plasmas. Nothing that I want to say today addresses this argument between two belief systems. I only hope to present experimental evidence, facts that we can handle and deal with. I don't believe the controversy will ever be resolved as long as we continue this debate above the line in terms of two different belief systems. One must do experiments, one must determine results with facts and debate the facts. Facts, unfortunately, are known, as always, with certain associated errors, certain uncertainties, and I'll go through a little bit our error analyses, just so that you can get the feel that we understand what we're doing and are handling the errors in a reasonable way. But I'm most interested in presenting the results and not in presenting an error analysis. The sources of uncertainties in these experiments can be loosely categorized into three groups. There's a measurement uncertainty, the uncertainty of each individual measurement in terms of the calibration accuracy. One of the things that's difficult about these experiments is that we're doing single sample experiments. In the presence of excess power, we make a measurement, the experiment moved on, we make another experiment, each measurement is a single sample. We cannot repeatedly measure the same observation in order to get a statistical understanding of the uncertainties of that measurement. Nevertheless, we can measure the propagation of that error as it reflects on the excess power. Systematic errors are a potential source of difficulty in our results. I mentioned at the outset that I believe our experiments either indicate a real unknown power source in the experiment or some very obtuse artifact in the measurement system. And if we're going to look for this obtuse artifact, it needs to be in the category of systematic errors. The way we designed our experiments and designed our calorimeter was intentionally to make it as simple as possible, to make the measurements as redundant as possible, to make the experiment as insensitive to drift as we could, knowing that these experiments would last for very long periods of time. And where we anticipated the existence of a systematic error source, we designed the calorimeter in such a way that the observation of excess power would yield a conservative estimate in the presence of such a systematic error. There are some transient corrections which can be made to the data due to the departure of the system from its steady state, and the equation I'll show you for the calorimeter is a steady state equation. And there are corrections that can be made as the system departs from its initial state, as the gas volume pressurizes, as the recombiner in these experiments works in an intermittent way. And I'll describe these a little bit. Important things to note are the effect on the energy determination, which is what we're leading to at the end of the day. Measurement uncertainty propagates an uncertainty in the measured energy in a calculable way. Systematic errors, of course, since we don't know what they are, or we would have corrected for them, propagate errors of either sign and unlimited extent. The transient corrections that we apply integrate to zero if the final and initial states are the same. The equation for the calorimeter is defined here. Basically, we have an isothermal flow calorimeter. We have a flowing aliquot of fluid past the electrochemical cell. The fluid is at heat capacity Cp, flowing at a flow rate dm dt m dot. There's a conductive loss term, since the heat of the fluid flowing out of the calorimeter will be heated above that of the environment. I'll get to this equation later. I should have put this a little later. In fact, I will. Let me just back off this for a second until I show you more particularly what the experiment looks like. What we wanted to do was design a simple system based upon well-established principles and operate as closely as possible in its steady state. If only because it's easier to describe to people what you've done. If you have a simple system, a steady state is more easily described. We wanted to maintain complete control of the operating parameters, where one of the operating parameters of an electrochemical system is the cell temperature. We felt that we needed to accommodate a very large dynamic range of the heat input and output, a range in the calorimeter from 1/10 of a watt to 100 watts, stable operation for months, online monitoring of all of the relevant variables, including the deuterium to palladium ratio, which we believe to be important in producing this effect. We wanted to make multiply redundant measurements of the parameters critical to the calorimetry, in particular of the temperature. We wanted to accommodate a large dynamic range, and we wanted to maintain the accuracy and precision, particularly the accuracy of the measurements, at better than 1 part per thousand. As I said before, we wanted to make the known sources of systematic error yield conservative estimates of the output heat. We chose to use a flow calorimeter consisting of a container with an approximately adiabatic wall through which we pump the calorimetric fluid at constant rate, and the container is maintained in a constant temperature bar. The electrochemical cell gives up heat to the flowing heat transfer fluid, and we measure the temperature of this flow at the inlet and the outlet. So the sensitive parameters, the parameters which might be subject to systematic errors, the inlet temperature, the outlet temperature, the mass flow rate, so that the power measured by such a calorimeter, the heat capacity of the fluid, the mass flow rate, a conductive loss term as that fluid loses heat to its environment, the inlet and outlet temperatures. This is the only equation which governs the steady state operation of this calorimeter. What we need to do is what we did was take a large bath that's about a meter huge, in fact. You're looking at it from the top. The bath maintained at constant temperature with respect to heaters on the walls. We place in this bath up to 4 calorimeters in a well-stowed environment. The bath is maintained plus or minus 3 millidegrees long-term and short-term. If we look at this thing in profile, seeing 2 calorimeters, and with this dimension now of the order of a meter, 2 flow calorimeters side by side, suspended above the bottom of the well-stirred bath. The flow is drawn from the bath, past 2 inlet temperature sensors, past the electrochemical cell which is placed in this environment, out past 2 outlet temperature sensors, platinum resistance temperature devices, RTDs, and in many of the experiments that I'll describe, also 2 thermistors were placed in that volume and pumped by a constant flow rate pump. If you look at a slightly greater detail of the electrochemical cell, here is the same device with the feet which maintain it above the bottom of the bath. 2 inlet sensors in this manifold. I'll show you the outlet manifold in a second. The electrochemical cell placed with the heat transfer fins in the radial direction so that the flow comes from the bath, past the cell, through the annular space between the cell and this evacuated silvered dewar, maintaining the constant temperature boundary, and past the 2 outlet temperature sensors. One of the very important things that you must do is ensure that the temperatures that you measure are accurate representations of the average temperature of the flowing fluid. You must well mix the fluid flow, particularly before the outlet sensors, so that you measure a good average temperature. Here's the outlet temperature manifold, 2 temperature sensors, and the fluid flow. I'll show you the fluid flow path. So what we have here is the bath, reduced now to 1 calorimeter for simplicity. The fluid flow, goodness gracious, that's an old slide. Sorry, I picked up the wrong slide, but it tells the right story. There's a pump, constant flow rate, constant displacement pump. The fluid is drawn from the calorimeter through a volumetric flow rate determination onto a computer-controlled balance to measure dMdt as the computer repeatedly polls the balance to determine the mass flow rate. This drying agent relates to experiments that were done with silicon oil, which had a capacity to pick up water, and do not relate to our present experiment. Parameters measured by the computer and the parameters controlled. We measure the voltages at the calorimeter boundary. The way we run our experiments is to run an isothermal condition. That is, a heater wound symmetrically with the electrochemical cell applies power so that the complementary power, you can just see the space for the helical grooves of a heater which is wound in this direction. The computer supplies power to the heater and to the electrochemical system, such that the sum of the 2 of them is held to be constant. In this way, we maintain constant power to the contents of the calorimeter, and the system will be isothermal, provided that there is no excess power source. The important thing here only is to measure your powers accurately. So we measure the voltages at the calorimeter boundary, the voltages for the heater at the calorimeter boundary, and also measure a reference electrode. We measure the two currents to give us the input powers, the power being the product of the current and the voltage to the cell and the heater. The temperatures, the bath and RTD, the inlet temperature 2 RTDs, the outlet temperature 2 RTDs and 2 thermistors. We also measure the room temperature. We measure the cell pressure, the volumetric flow, the gravimetric flow, and a multiplexed measurement between two electrochemical cells run in parallel. We also measure the palladium resistance, which is multiplexed to the resistance measuring device to give us the deuterium to palladium ratio. We control the cell current and the heater current in such a way that the sum of the two input powers is held to be constant, and we, under some circumstances, control also the bath temperature. I don't want to overburden you with this issue of sources of error, but it's important to consider what potential sources exist in such an experiment and look at the means by which you can come to believe that they're not important. The output power, as I said before, is described by this equation in terms of the heat capacity of the flowing fluid, the inlet and outlet temperatures, and the conductive loss term. The input power is the sum of the power applied to the heater, the power applied to the electrochemical cell, which is simply the current, the product of the current and the voltage. All of our electrochemical cells are closed. And any excess power source that you may have in the system. As it happens, these powers are measured as the product of two voltages divided by the resistance, which is used to measure the current flowing to that element. Same here. For the electrochemical power, the product of the voltage at the calorimeter boundary, the voltage across the resistance measured, used to measure the current flowing to that element. Temperatures are measured with platinum resistance temperature devices, so they are measured in terms of the resistance of the RTD element, normally something like 100 ohms, where the coefficient alpha is the known slope of the temperature resistance coefficient of platinum. So that in terms of the raw measured data, the excess power is expressed this term due to the conductive transfer of heat out of the electrochemical environment. The resistance ratio of the inlet and outlet temperature sensors minus the known sources of input power. This particular term in square brackets has useful properties. This resistance ratio difference has a wonderful effect in reducing susceptibility to systematic errors. We have, therefore, three types of terms in this expression. The constants, which are predetermined, the heat capacity, temperature coefficient of resistance of platinum, the initial resistances of the temperature measuring devices, and the resistances used to determine the currents flowing in the electrochemical and heater power circuits. The calibration constant, the conductive loss term from the calorimeter, which is a small term, but one which is calibrated at the beginning of the experiment and repeatedly calibrated throughout an experiment. And the variables that are measured, the mass flow rate, the resistance of the inlet and outlet temperature sensors, and the 4 voltages. We're looking for potential sources of systematic error in these terms. Temperature coefficient of platinum, we expect to know source of error and do nothing about it. Heat capacity, in our more recent experiments, In fact, all but one of the experiments that I will describe the results of, water was the heat transfer fluid. Its heat capacity is well known, and its temperature coefficient of that heat capacity is well described. In days when we were using silicone oil as a heat transfer fluid, and only one experiment will be described of this type, it did have the tendency to pick up moisture from the air, changing its viscosity and its heat capacity, and efforts had to be made to keep the water content of the silicone oil down. Temperatures measured through these resistance ratios, well, it's based upon a platinum element. To the extent that these elements are attacked by corrosion, then there might be some source of systematic error. Again, the currents determined via the standard resistances, the temperature coefficient of these resistances might lead to systematic errors, and attention must be paid to them. The conductive loss term can be affected by poor mixing. It's important to ensure that that there is some form of turbulence remover before the temperature measurement, particularly at the outlet. There might be some absolute error in the multimeter calibration. The way we perform our experiments, we use a single calibrated multimeter, and all measurements are multiplexed to that meter. We periodically interchange that meter with another calibrated multimeter, and we in general run two electrochemical cells, two calorimetric experiments in series. So one, in fact, acts as a blank with which we can refer the other. If we observe excess power in one, while we're not observing excess power in the other, then it's unlikely to be a source of poor calibration of the multimeter, and we must look to other sources of potential systematic error. The 4 voltage terms, well, we know how to measure voltages reasonably accurately, and we can periodically interchange the multimeter, the digital voltmeter, in order to ensure that this is not a source of systematic error. The mass flow rate, as I described to you, is measured by simply pouring the fluid into a volume on a digital balance and periodically pulling the variant. Having described to you some of the sources of error and the means by which we have attempted to remedy them, I will now describe to you our results. The results here are shown as just a limited range of experiments. We started in April of 1989 with 2 experiments operated at 1,000 psi of deuterium. We observed apparently excess power in both of these experiments. We then attempted a series of high-pressure experiments which, for technical reasons, never attained the durations that we had hoped. And we observed no excess power in these high-pressure experiments. We then went for a rather unfortunate period of something like 7 months here in 1990, where we observed no excess power. We then began a series of experiments which I'm going to describe, beginning with P12, in which all during this time we've been doing our degree of loading experiments, trying to understand the parameters by which you can come to load deuterium into the P12 was the first experiment in which we had identified aluminium and also possibly silicon as species that were desirable for forming films on the surface of the palladium, which would allow one to attain and maintain periods of loading. P12, I'll briefly describe the results of. It's the first experiment in this series in ambient pressure cells in which we observed excess power. P13 was a light water replicate which went for a similar period of time. No excess power was observed. We then attempted to replicate P12 in a series of experiments, 13, 14, 15, 16, and 17, and observed excess power in each of those experiments, each of them heavy water experiments. P18 was a special experiment and in fact failed within about 80 hours of its operation. We began another series of experiments in which boron was added to the electrolyte. I'll describe P19 result because it's a special result, And the most recent experiments, C1 and C2, were experiments in which we're attempting to vary the surface to volume ratio to try and find out whether the effect that we're looking at is a surface effect or a volume effect. All of the experiments that I'm described up to C1 were performed with 3mm Engelhart's palladium from a single stock, heat treated in each case in an identical fashion. Experiments that were by and large performed in an electrochemical environment that looked like this. 3mm palladium cathode, either 3 or 5 centimeters long, helically wound platinum anode, 1 molar LiOD electrolyte, to which additions were made of the elements aluminium, silicon, and in some experiments boron. This is mounted inside a pressure vessel so that we can apply small overpressure of deuterium, and the pressure line connected to a pressure transducer, which is sitting above the level of the electrochemical experiment. This is the result that we obtained in P12. These are raw data and not subjected to the error analysis that we've applied the later data to. It was the first major result that we achieved in ambient pressure experiments, and one that I'm, for historical reasons, happy with. Here we observe a time when the current density was ramped through little hiccups, which were largely due to miscommunication with the technician more than anything else. The excess power for the two independent pairs of temperature sensors is plotted at the top. You can just distinguish, perhaps in a somewhat fuzzy presentation, the two different pairs of temperature sensors, but they're statistically not distinguishable. This is a period of time of 8 days from here to here, an observation of the order of 1 megajoule, representing something like 30 megajoules per mole of palladium in that observation. The first time we achieved a result in ambient pressure cells, and the first time we obtained a result with aluminium additions to the experiment. This time here is 1,200 hours into the experiment. Replication was attempted for a light water cell. Here I show a period of time just to show you what an observation of no excess power looks like, which is the normal condition of our experiment. We observe a period when the current is ramped to high levels. The data here show the total power observed in the experiment. This little blip here is the time when the heater was stepped up and down for calibration purposes. The excess power in this experiment sits very, very close to the baseline. The excess power is a line which fits on the baseline. The heater here is stepped up for a small period and down. P13 ran for 1,300 hours, was in thermal balance for the entire duration of that experiment. Now P13, the light water replicate of P12, was in the calorimeter at the same time as a new experiment, P14. P14, identical in all respects to P12, the heavy water cell. In this case, P12 had a surface treatment which involved helium-4 implantation. P13 had helium-4 implantation. P14, which is shown in the cell, had helium-3 implantation but was otherwise identical. Here is the same block of time. The heavy line represents the raw data for the 2 pairs of temperature sensors for P13, with the measurement uncertainty expressed by this light grey hatched region, showing that the excess power for P13 for this particular period of time is 0, plus or minus a small uncertainty in the energy for this period of time. And the calorimeter at the same time, electrically in series and powered from the same current source, was P14. And for the same period of time, we observe this form of excess power, 0.21 megajoules, plus or minus its assigned uncertainty, at a time in response to the current ramp shown. So here we have a case where the calorimeter was under identical conditions. The two experiments were side by side and the calorimeter being measured with the same measurement devices, and we observe excess power in a heavy water cell, but we did not observe it with the light water cell. This is a rather small observation of excess power. The energy under this, as I showed before, as I said before, is of the order of 0.2 megajoules with its assigned uncertainty of the amount denoted. One of the important things to note in these experiments is that we, in general, don't observe excess power on the first observation, on the first attempt. This is a typical experiment, probably one that's never been performed. You calibrate the experiment with controlled heater steps at a time when the electrochemical power is low. Then we will start by stepping the total power, that is stepping the heater to some high value, and then you will start to ramp the dashed line, the electrochemistry. On the first attempt, you will not see any excess power in general. On the second attempt, you may not. But when the initiation period that I described as the time has elapsed, on, for example, the third observation, as we ramp the electrochemistry at some critical current, we may begin to observe excess power in the sense that the output power determined by the calorimetric equation is larger than the input power. If you remember the equation of the calorimeter, I'm going to show you a time when, for a particular experiment, P15, a replication of P12, we ramped the current density for a particular interval of time, and the mass flow rate for the calorimetric fluid going into the calorimeter was held relatively constant. As a consequence of this current ramp, the resistance ratio for P15, which was in the calorimeter at the same time as P16, resistance ratio fell to a value of about 1.55, corresponding to a loading of about 0.96. The mass flow rate was held constant, and here we have the total power held by the computer to be essentially constant at 10 watts, and then steps to 12 watts this time. As the electrochemistry was ramped, the product of the current and voltage increasing, the heater is shut off by the computer just to hold, the sum of the two to be constant. For this period of time, the inlet's temperature sensors, as usual, were constant, the temperature of the bath being constant, so that the inlet temperature was 35.568 plus or minus a few millidegrees for this period of time. As I described before, if the input power is constant, the mass flow rate is constant, the inlet temperature is constant, then the outlet temperatures must be constant. In this case, we observe the outlet temperatures, sensors, the two of them, sometimes they move apart a little bit and you can see the variation. The two outlet temperature sensors were not constant for this period of time, suggesting that within the calorimetric boundary, there is a source of unaccounted for excess power. And if we calculate that from the equation, we can see this effect. Now, and this is the result that I showed you before in the introduction. We have an excess power of the order of 1 watt, increasing to a value of 3.5 watts. This time here, the total power in the system was stepped from 10 watts to 12 watts. And this effect represents as much as 28% of the input power. Just to see what sort of effects we're talking about, however, I show you the total power here and the excess power. So the effect is observable. The measurement uncertainty is defined and small with respect to this observation, but we're still looking, in this case, at an effect which is only, 20, 30% of the total input power. I'm going to give you at least one example of other than baseline power observation. As I said, we've observed this sort of effect on something like 38 occasions. We started to add boron for good reasons, and if anybody asks later, I can give you the reasons for it. First thing we observed in cells to which boron is added to the electrolyte is boric acid. The boron goes into the metal and affects the resistance ratio. So here we have a time at which we've first stepped the current down to low values, reversed the current. The cell voltage follows this profile on the reference voltage. The interesting thing is that instead of the resistance ratio going back over its, so the resistance ratio versus loading curve look like this. As we strip the cell, we expect to see the resistance go over its maximum and come back down the other side. Instead of doing so, in the case of cells to which boron has been added, we see two maxima during the stripping and two maxima again during the reload. This value, the deuterium, should be about 2. You observe that in the cells to which boron is added, that value is 4. This is still hard for us to explain. It's nevertheless a very well reproduced observation. More interesting still, perhaps, and here we show data for the raw measurements of two RTDs and 2 thermistors. This is the same current reversal that I showed you before, followed by a current ramp. The excess power, in fact, unbeknownst to us, had initiated at low current. We were starting to observe excess powers of the order of 0.3 to 0.4 watts before the current reversal. During the period of the stripping, the excess power actually comes back down towards 0, but restores itself. In an attempt to increase the excess power observation, we ramped the current, and the excess power is very little correlated to the current density in this case. This is one of the observations that I described as a burst, being uncorrelated to the parameters that we have ourselves under control. We have data from 2 RTDs and 2 thermistors. The 2 thermistors do in fact show some sort of systematic variation, but apart from that, that small glitch here, all 4 temperature sensors see essentially the same result, and the excess power calculations are the same. Power input at that stage. In fact, I'll get to that point on the next slide. This was a time in which we had prepared the calorimeter to be ramped. The calorimeter was set at 14 watts of total power, whereas there was very little electrochemical power because the electrochemical current was only 0.1 of an amp. If we normalize the observation in this case to the total power, however, because we had 13.7 watts of heater and 0.3 watts of electrochemistry, the normalization of the excess power observation to total power is a small percentage. And here we have the measurement uncertainty reflected. To observe the effect of the heater, we stepped the heater down at this point, which did not affect the excess power, but affects its percentage, of course. So normalized to the total input power, we have at most a 12% observation. You would normalize to the total power if you thought that the effect had something to do with the heater or with some form of artifact. In this particular case, if you normalize to the electrochemical input power, obviously we'll get a much larger effect, and we have an effect something like 250% of the electrochemical input power, with the uncertainty now expressed in terms of a percentage of the electrical input power is a larger number, but nevertheless a small number compared to the observation. I wanted to finish up here with our summary of observations. Unfortunately, there's a lot more that I really need to say. One of the things which I wanted to show you is from one of the more recent cells, we were able to observe the correlation with statistical significance between the excess power observation expressed in terms of watts per cc and the loading. And I fitted three functions to this. So excess power, loading determined by the resistance ratio. I fitted three functions, and you can clearly not distinguish between them. An asymptotic function, asymptotic to a loading limit of 1, which you might expect if the parameter that we're observing is correlated to the activity of deuterium in the lattice. An exponential function, which you might expect if the observation of excess power is correlated to the population of a higher energy state, such as occupation of the tetrahedral sites in a Boltzmann distribution. And a parabolic function, which you might expect if the excess power observations are somehow correlated to two atomic interactions, the possibility of two species getting together above a critical threshold. The data are simply not good enough to distinguish between them, but there's clearly a correlation between the excess power observed and the loading. And I'll just summarize our observations from these cells, and we'll be happy to provide experimental support for some of the conclusions which I haven't yet given you. Basically, we have observed more than 350% excess power in a burst mode as correlated to electrochemical input power. We observe 5 to 50% baseline effects with, in terms of a measurement uncertainty, somewhere between 8 and 90 sigma observations. We observe these effects in each instance of excess power observation in the range 0.1 to 1 megajoule, and that's between 10 and 100 times the sum of all of the chemical reactions that, the known chemical reactions that may occur in the cell, given the chemical inventory that we have. We observe more than 45 megajoules per mole of palladium, corresponding to something like 450 eV per atom. 200 watts per cc of excess power for an experiment which has a small number of cc's. Internal repeatability correlated strongly with the deuterium loading. Experimental reproducibility in the experimental sequence P12 to P17, one of which was a light water cell. All of those experiments produced excess power when performed similarly to the prototype experiment P12. We never observed negative excess. If you were thinking of certain classes of systematic error that might occur, you might think that they would occur as equally in the positive direction as in the negative direction. We never observed negative departures from the thermal balance of the system except under transient conditions. Excess power has not been observed with light water, and light water has been observed to terminate an excess power observation, and observations were being made in heavy water cells. And we observe excess asynchronously in series cells, suggesting that measurement errors due to drift in the multimeter are not themselves sources of the error. There's a reproducible pattern. We don't observe excess for a certain initiation time. In general, the excess increases with time until the deuterium to palladium ratio is lost, and we think this is a feature of contamination of the surface with undesirable species, so that we can no longer achieve the electrochemical conditions necessary to achieve the loading. We've observed excess heat, similar characteristics in two different types of calorimetric cells, two different types of calorimeter. And in conclusion, we presently are unable to account for the observed excess temperatures by any artifact that we have considered. And you cannot account for the measured excess heat by any chemical or mechanical process with which we are